Electric aviation's future hinges on overcoming battery challenges. Can we rise to the occasion?
Age of electric aviation, a world with quieter, cleaner skies and completely new ways to get around. But is this dream actually ready for takeoff, or is it still kind of stuck on the runway? Let's dive in.
Seriously, just imagine it for a second. Skipping all that traffic, just flying over the city in a quiet electric air taxi. Now, this isn't some sci-fi fantasy anymore. It is the very real goal that dozens of super innovative companies are racing towards. And if you want to know just how real it is, you just have to look at what some of the leaders in the space are already doing.
I mean, take a look at Joby Aviation. These guys went from a simple concept in 2009 to actually delivering their first aircraft to the U.S. Air Force in 2023. And get this, they're aiming to launch a commercial air taxi service in 2025. That is next year. So the dream is absolutely taking shape. But the entire industry, all of it, hinges on solving one single monumental challenge. And yeah, you guessed it, that challenge is the battery. It is, without a doubt, the single biggest thing standing between us and a sky full of electric planes. And to really get why, we need to talk about something called energy density. Okay, this line just nails the problem perfectly. Jet fuel is, well, it's kind of like a magic potion of energy density. It packs an unbelievable punch for how little it weighs. Batteries, on the other hand, are just heavy. To get the same amount of juice as just 36 kilograms of jet fuel, you'd need a battery that weighs over 600 kilograms. That's a huge difference. Now just imagine what happens when we try to scale that up for a real passenger jet. The result is absolutely staggering. To replace the fuel for just one long-haul flight, you would need a lithium-ion battery weighing 1,560 tons. I mean, let that sink in. That's more than the maximum takeoff weight of 3 entire Boeing 747s. The physics, right now, just don't add up for long-haul electric flight. But you know what? The weight problem doesn't even end there. There's another, more subtle layer to it. Someone in an online discussion really hit the nail on the head. A plane burning jet fuel literally gets lighter as it flies, right? Which makes it more efficient. A battery, though, weighs exactly the same whether it's fully charged or completely dead. That means you're hauling all that dead weight from the second you take off to the moment you land, which just crushes how many people or how much cargo you can carry. Okay, so we've seen the big macro problem of just sheer weight. But beyond that, there's a whole microscopic battle happening inside the battery itself. See, they don't just store energy, they degrade, they age, and they lose their ability to work well over time. And to keep track of this really critical decline, engineers use a very specific measurement. It's called state of health, or SOH. The easiest way to think about it is like a battery's personal health score. A brand new battery is at 100% SOH, but every time it's used and recharged, that number drops, meaning it can't hold as much charge or deliver as much power. Now, for an airplane, where performance is literally a matter of life and death, being able to predict and manage SOH is absolutely critical. And this is where things get really, really tricky. Unlike a fuel tank, which is pretty simple, it's either full or it's empty, a battery's decline is this complex, non-linear mess. It's a dynamic, chemical system that's constantly changing, and that change is driven by a few key, invisible forces. So this degradation basically happens in a couple of key ways. First, you've got loss of lithium inventory. That's where the little ions that carry the charge literally get trapped and taken out of the game. Then there's loss of active material, which is where the physical guts of the battery start to crumble and break down. And then on top of all that, you have something called calendar aging, which is the crazy fact that a battery gets worse even when it's just sitting there doing nothing on the tarmac. That's a huge problem for any kind of transportation fleet. Now, these huge challenges have kicked off this sprawling, super competitive ecosystem of companies all racing to find a solution. This isn't just one company tinkering in a garage. This is a global web of specialists, investors, and even fierce rivals who are all surprisingly interconnected. Let's just use Archer Aviation's Midnight aircraft as an example of how collaborative this whole thing is. So, Archer designs the plane itself, but then the car giant Stellantis comes in as a key investor. A company called Molicel provides the actual battery cells. KULR handles the safety solutions. The aerospace titan Boeing provides the self-flying tech, and even NASA is partnering with them to certify the whole system. But this big web of teamwork isn't always so friendly. In fact, it can get downright hostile. Back in 2021, Wisk Aero, which is actually owned by Boeing, sued Archer, accusing them of stealing trade secrets. The whole industry just watched as two of the biggest names went head-to-head in this high-stakes legal drama. But then, in a twist that honestly nobody saw coming, they settled. And not only did they settle, but Boeing actually invested in Archer, and Wisk became Archer's exclusive partner for autonomous flight tech. So boom, fierce competitors became critical partners. It just goes to show how intertwined this whole new market is. Turns out everybody kind of needs everybody else to succeed. But the story of the battery doesn't just end when it's not good enough for a plane anymore. An aviation battery might be retired when its state of health drops to, let's say, 80%, but it still has a ton of life left in it. And this raises a huge question about sustainability and what on earth we're going to do with this coming wave of used-up batteries.
And the scale of this is it's immense. By 2030, analysts figure that over 1,400 gigawatt-hours worth of EV batteries from cars alone are going to be retired every single year. Now imagine adding all the aviation batteries to that pile. It's a massive amount of valuable but also hazardous material. Just throwing it in a landfill is not an option, so the focus has totally shifted to recycling.
But here's the thing. Not all recycling methods are created equal, not even close. The oldest method, pyrometallurgy, is basically just melting everything down in a giant furnace, and it actually has a negative environmental impact. Hydrometallurgy, which uses liquids to pull out the metals, is better. But the real holy grail is something called direct recycling, a method that actually preserves the complex, valuable materials inside and offers by far the biggest environmental benefit.
And all of this has kicked off a whole new wave of innovation. You have companies like Tesla and Redwood Materials building these closed-loop systems. You have others using tech like blockchain to create battery passports that can trace materials from the mine all the way to the recycling plant. It's all part of this massive effort to develop smarter recycling and more local supply chains to create a true circular economy for batteries.
So when it comes down to it, the challenge of electric flight isn't just about getting planes off the ground. It's about creating a sustainable, circular system that can power this whole new era of transportation for decades. The tech is moving at an incredible pace, for sure, but the biggest question is still out there. We aren't just building the future of flight, we're building its foundation. So, are we going to build it?